A chess player sits across the board. She surveys the position rooks, knights, pawns, the opponent's king exposed. She makes a move, not because a teacher told her this is the correct move, but because millions of previous games taught her that this position, this move, leads to winning more often. She learned by playing, experiencing wins and losses, and adjusting her strategy. Reinforcement learning is this process. An agent learns to make decisions by interacting with an environment and receiving rewards. The reinforcement learning framework has 4 elements: the agent, the decision maker, the state, the current situation, the action, what the agent does, the reward, the feedback. The agent's goal: maximize the cumulative reward over time. This isn't supervised learning. No one tells the agent the correct action. And it isn't unsupervised. There is feedback, just delayed and sparse. The policy is the agent's strategy, a mapping from states to actions. A deterministic policy says, in this position, make this move. A stochastic policy says, in this position, make move with 60% probability and move B with 40%. Policy is the learned behavior, the chess player's intuition distilled into a function. The goal of rule is to find the optimal policy, the strategy that maximizes expected cumulative reward across all possible states. The value function evaluates positions. V of S under policy pi equals the expected cumulative reward starting from state S and following policy pi thereafter. IV means the position is advantageous. A low V means trouble. The Q function goes further. Q of S equals the expected reward from taking action in state S and then following pi. V evaluates positions. Q evaluates specific moves in specific positions. The exploitation trade-off. Always choose the action with the highest estimated Q exploitation, and you might miss a brilliant move you've never tried. Always choose random actions exploration, and you never capitalize on what you've learned. Epsilon-greedy. With probability 1 minus epsilon, pick the best known action. With probability epsilon, pick randomly. Start with high epsilon, explore widely. Gradually reduce epsilon, exploit more as knowledge accumulates. A reward received now is worth more than the same reward received in the future. The discount factor gamma, between 0 and 1, controls this. Gamma near 1, the agent cares about the distant future, critical for dosing, where a dose today affects toxicity next month. Gamma near 0, the agent is myopic, only immediate rewards matter. For drug design, gamma is typically close to 1 because the final molecule's properties are all that matter. Agent, state, action, reward, the role framework. Policy, the learned strategy. Value and Q functions evaluating positions and moves. Exploration versus exploitation, trying new things versus using what works. Discount factor, how much the future matters. Next, the algorithms that learn the optimal policy.